Here we have the definite integral of the absolute value of x squared minus 4. And this definite integral right here, it represents the area between the graph of the function absolute value of x squared minus 4 and the x-axis from negative 2 to 4. And this is what the graph looks like. So this is the graph for the function absolute value of x squared minus 4. And to find the area of the shaded region, we have to break it up into two regions. The first one will be from negative 2. It looks like negative 2 to 2, and then 2 to 4. And so let's set up the integrals. So we'll end up with two integrals, two definite integrals, one definite integral for this region, and then one definite integral for this region. And so first we need to get the antiderivative for the function f of x equal to the absolute value of x squared minus 4. And so first, let's rewrite this using the definition of absolute value before we can find the antiderivative. And so by definition of absolute value, this is equal to x squared minus 4 if x squared minus 4 is greater than or equal to 0. And then this is equal to negative the opposite of x squared minus 4. And let's go ahead and simplify this. This is negative x squared plus 4. And then if x squared minus 4 is less than 0. And so this by definition of absolute value. And then we need to solve this. This is called a quadratic inequality. So let's go ahead and solve this inequality. So this is called a quadratic inequality. So we need to solve it. So to solve this type of quadratic inequality, what we do is this. Go ahead, we first factor the left side. So it's x minus 2, and then x plus 2. And then this is equal to 0. And then next, write the corresponding equality. So the corresponding equality, just make it equal to 0, and then solve right here. So we get x. So we get x minus 2 equal to 0, or x plus 2 equal to 0. And then right here, add 2 to both sides. So we get x equal to 2. And here, subtract 2 from both sides. So we get x equal to negative 2. And then graphically, this is what it looks like. And so let's go ahead and graph this part right here on the graphing calculator. So we graph it on the graphing calculator. This is what it looks like. So this is negative 2 and this is 2. So negative 2 is right here and then 2 is right here. And so now we have three intervals. The interval from the left side to negative 2 and then negative 2 to 2 and then 2 to the right side. So we end up with the intervals negative infinity to negative 2, and then we have the interval from negative 2 to 2, and then we have 2 to infinity. And since this is greater than, then is the interval, the outside intervals that will contain values that would make this inequality true. And if we look at the graph right here, the interval from negative infinity to negative 2, the graph is above the x-axis. And so that's where the x squared minus 4 is greater than 0. And then the interval from 2 to infinity, that's where the graph is above the x-axis. And so that's where the x squared minus 4 is greater than 0. And then the interval from negative 2 to 2, that's where the graph is below the x-axis. And so that's where so from the interval from negative 2 to 2, that's where this inequality is less than 0. But here we want greater than 0. And so the solution solutions to the inequality, the quadratic inequality, the solution to this inequality right here will be the true intervals. And so normally we write it like this: is the first interval and then union with the second interval. Because these are the intervals where this interval, this is where the graph is above the x-axis. This interval, that's where the graph is also above the x-axis. And since we have a greater than or equal right here, and so to be technically correct, we need to write this like this. And so this is the solution to this the solutions to this inequality. And it'd be from negative 2 to negative infinity to negative 2 and then 2 to infinity. Now other quadratic inequalities, x squared minus 4 less than 0, and so it'd be the middle interval. And so we need x squared minus 4 less than 0. Then solutions to the inequality less than 0, it'd be the middle interval, which is the negative 2 and so again, if we graph x squared minus 4, then this is what the graph looks like. And then the part that is below the x-axis is from negative 2 to 2. And so that's how we know that the solution to this, to the solutions to the inequality x squared minus 4 less than 0 is negative 2 to 2. And now let's get back to our integral problem. And so from here we can write that the function absolute value of xy minus 4 is equal to xy minus 4 if x is in the interval from negative infinity to negative 2 or 2 to infinity. And then this right here is equal to negative xy plus 4 if x is between negative 2 and 2. And then now we need to look at we can look at the graph, the shaded region right here, and then so we can figure out how to help us set up the integrals. And so from negative 2 to 2, we need to use this equation right here for the integral. And then from 2 to 4, which is in here, and we will need to use this equation. So one more time, to set up the integrals, the first region is from negative 2 to 2. And from negative 2 to 2, we will use this as f of x. And then the second region is from 2 to 4. And 2 to 4 is in here. And so we will use the xy minus 4 to set up the integral. And so this, the definite integral right here, will equal. So first we need to go from negative 2 to 2, and the function will be negative x squared plus 4 dx. And then the second integral will be from 2 to 4, and from 2 to 4 is in here in this interval, and therefore we use the f of x will be xy minus 4. And so that's how we would set up the two integrals. So this integral is the area of this region, and then this integral is the area of this region. And then now we need to find the two integrals, two definite integrals. And so let's do the first one. And so for this definite integral, the antiderivative, and again, by the fundamental theorem of calculus, it says that this is equal to the antiderivative evaluated at 2, and then minus the antiderivative evaluated at negative 2. The antiderivative of x squared, again, add 1 to the exponent, and we get x to the third, and then divided by 3. And then antiderivative of a constant is just the constant times the x. And then now we need f of 2 and f of negative 2. And then we also need negative 2. And then we can evaluate this on a scientific calculator, and that will come out to be 16/3. And then this one come out to be negative 16/3. And so this will equal to 16/3, and then minus negative 16/3. And this would be 32/3. And so the area for the first definite integral is 32 thirds. And then now we need the area of the second definite integral. And so again, right here, fundamental theorem of calculus says that this is the antiderivative at 4 minus antiderivative at 2. So for this particular integral, the integrand is xy minus 4. So the antiderivative at 1 to the exponent, we get x to the third, and then dividing by 3. And then antiderivative for the constant is 4 times x. And then we need f of 4. And then we need to evaluate the antiderivative at 2. And then simplify on a scientific calculator, and we'll get 16 thirds for f of 4, and then f of 2 we get negative 16 thirds. And so this right here will be 16 thirds minus negative 16 thirds. And this will also be 32 thirds. And so the area of the second region is also 32 thirds. And so the first integral is 32 thirds, and then the second integral is 32 thirds. And so this becomes 64 thirds, or 21 and 1/3. And so the area of this region is 32 thirds, and the area of this region is also 32 thirds. And so together is 64 thirds, or 21 and 1/3. And that's what when we fill this up with 500 rectangles, then the program here says that it's 21 and 1/3 basically. And so the area of this shaded region right here altogether is 64 thirds, or 21 and 1/3.